Look at this diagram of the human body's gravitational exposure. Right now, the top of your head is aging faster than the soles of your feet. Gravity is slightly weaker at your head than at the bottom of your body, and that tiny physical difference means time passes fractionally faster for your brain than your toes. The navigation app on your phone relies on GPS satellites orbiting 20,000 kilometers above the Earth. If engineers did not account for the fact that time runs differently in orbit than it does in your pocket, the coordinates would drift by 11 kilometers every single day. We treat time as a universal metronome, ticking away exactly the same for everyone, everywhere. But the physical reality is that time is a localized physical property. It stretches and compresses depending on exactly where you stand. In 1905, Albert Einstein published his special theory of relativity, establishing a rule about the structure of the universe. The faster an object moves through space, the slower it moves through time. 10 years later, he introduced general relativity. This animation shows space-time as a four-dimensional fabric warping around a massive sphere like the Earth. The deeper you sit in that gravitational dent, the slower time passes. If the passage of time depends entirely on how fast you are moving and how strong the gravity is around you, then an absolute universal second does not exist. It is a mathematical fiction. To test these equations, in 1971, two physicists packed 4 highly precise atomic clocks onto commercial Boeing 727 airliners. They flew one set of clocks eastward around the globe and another set westward. When they landed and compared them to a stationary master clock on the ground, the results matched the math exactly. The eastward flying clocks had lost time. The westward flying clocks had gained time. We see this same effect bombarding our atmosphere every day. When cosmic rays hit the upper atmosphere, they create subatomic particles called muons. These particles decay so rapidly they should never reach the Earth's surface. Because they travel at 99.9% the speed of light, their lifespan stretches out relative to our perspective, allowing millions of them to strike the ground. Up in orbit, a GPS satellite experiences a tug-of-war between these two effects. It sits in a weaker gravitational field than we do, which speeds its onboard clock up. But it also orbits the Earth at 14,000 kilometers per hour, which slows its clock down. When you calculate the net difference between those competing forces, the satellite's clock gains exactly 38 microseconds every day compared to a clock on the ground. That 38 millionths of a second is a constant correction factor built into the code of every single navigation system, your personal smartphone, and every delivery truck. Relativistic physics is a required component for our modern tools to function. This mechanical time dilation applies exactly the same way to human biology. In 2015, astronaut Scott Kelly launched into space, leaving his identical twin brother, Mark, on Earth. For 340 days, Scott lived aboard the International Space Station, orbiting the planet at over 27,000 kilometers per hour. Because he spent nearly a year traveling at that immense speed, Scott's clock ticked slower than his brother's. When he returned to Earth, he was 13 milliseconds younger than Mark. Our internal processes, from aging to cellular decay, are tied to the local rate of time. By moving through space at high speeds, you physically alter how quickly you move through time relative to everyone else. This diagram tracks the space-time paths of the twins, and it answers a famous logic puzzle. If both twins see the other as moving, why doesn't each think the other one is younger? The answer is that their experiences aren't symmetrical. The traveling twin has to accelerate, turn around, and decelerate, shifting into a different inertial frame of reference. Physicists push these mathematical boundaries even further, modeling paths through space-time that bend so intensely they form a loop, allowing an object to travel backward into its own past. Recent research into paradox-free time travel suggests that space-time can adapt to prevent logical contradictions. If a traveler went back in time to stop a disease, the math shows that events would reorganize themselves, ensuring the traveler still has a reason to go back while the disease is still confronted. This implies the universe remains consistent by allowing events to be both the cause and the result of themselves simultaneously. If you look closely at the equations of physics, they don't care which direction the clock runs. A mathematical model of two particles colliding works exactly the same whether time goes forward or in reverse. Our experience of a one-way street comes down to entropy. The laws of thermodynamics dictate that a closed system will naturally move from a highly ordered state into a chaotic, disordered one. Just as individual water molecules aren't wet, time may only be a phenomenon that appears when you zoom out to the macro scale. The numbers ticking on our watches are dictated by gravity and motion. Shrink down past a certain microscopic threshold, and those numbers cease to mean anything at all. If time stretches near massive objects, loops back on itself in equations, and disintegrates completely at the edges of reality, what exactly is passing when we feel time go by?